On this video, we're going to talk about section 1.3 in your book, Linear Functions. But before we get to that, I want to review a little bit of what we did on the last one. So if you remember, we said that the average rate of change, we will abbreviate as rock or a rock, either way. And we also talked about the fact that this can be written as delta y over delta x, that's the change in y, over the change in x. Hopefully from your Algebra 2 days you recognize that this is really the slope of the line joining 2 points that are on the function. And so we have seen it in our maybe familiar Algebra 2 notation, the y2 minus y1 over x2 minus x1, but hopefully we will at least become familiar, if we aren't already, with the functional notation f of b minus f of a over b minus a. So, for example, if we said our function f of x was 3x minus 2, and we said our a is equal to 1, and our b is equal to 4, then to find the average rate of change between a equals 1 for x equals 1 and x equals 4, we would say f of 4 minus f of 1 all over 4 minus 1. Now f of 4 we know is going to be, I'm going to write it out here, 3 times 4 minus 2. That's plugging in the 4 into our function. We're plugging the 4 in for x. I'm going to subtract from that, and I'm going to plug in the 1. 3 times 1 minus 2, and that's all over the 4 minus 1, which is 3. So it looks like the f of 4 is 12 minus 2 is 10, and the f of 1 is 3 minus 2 is 1, and this works out very nicely to be an average rate of change of 3. Now, let me change gears here a little bit, and suppose I have a generic function f of x. And I'm not going to tell you what that function is right now. Just imagine it's any function. And I'm going to say there is a point on that curve, the graph of that function, and it's going to have x-coordinate x, which will make its y-coordinate f of x. So if you want to think visually, imagine that our curve is doing something like that. There is our f of x curve, and I'm going to say right in here is a point, and its x value is x, and that means its y value must be f of x because it's on that curve. So that makes that point be x comma f of x. Now suppose I'm going to go a little ways away from that x. I'm going to go over a distance of, say, h to this point right here. So that is, and I'm assuming h is positive here, but it doesn't have to be. So I'm moving this point over a positive h there. H could have been negative and I could have gone left. And I'm going to call that x value x plus h. Now, my claim is that its y value, because it's on that curve, is going to have to be f of x plus h. And that makes the coordinates of that point x-coordinate x plus h and y-coordinate f of x plus h. Crazy. Now, the rate of change, the average rate of change, or the slope of the line joining those 2 points, that means the same thing. So our rate of change is going to be the change in the y values. So f of x plus h is that y value on the second point, minus f of x, which is the y value on that first point, all over the x value on that point was x plus h minus the x value on the other point. And so if you let those x's cancel each other out, we get f of x plus h minus f of x all over h. Crazy. So my claim is that is the same, just very crazy, maybe complicated function notation, but it is another representation for this average rate of change. So that's the first time we've seen this notation, but I got a feeling it's not going to be the last. Let's do an example of what that might look like. So let's say our f of x is going to be 2x plus 3. And let's see if we can find the average rate of change between the 2 points x comma f of x and x plus h comma f of x plus h. Crazy, crazy, crazy. Well, let's see. If the x value is x, and if this is our function, that means that f of x is going to be just the 2x plus 3. Okay? Oh, this is about to get really crazy. Now, if x plus h is the x value here, then f of x plus h means we have to plug in x plus h where we see the x. And so that is going to be 2 times the quantity x plus h plus 3. And if I distribute that, that will be 2x plus 2h plus 3. 2x plus 2h plus 3. Crazy. Now I'm going to take that and I'm going to do what we said for the average rate of change. We are going to take f of x plus h minus f of x all over h. So here's the f of x plus h, 2x plus 2h plus 3 minus, here's the f of x, 2x plus 3 all over h. Hope you're still hanging in there. I'm going to distribute that minus sign, 2x plus 2h plus 3 as before, minus 2x minus 3. That was supposed to be an h. Let me make it there. Okay. All over h. Now, always in these scenarios, this f of x plus h minus f of x minus h, anything that doesn't have an h in it is going to cancel. So that 2x and that negative 2x will cancel. That 3 and that negative 3 will cancel. And surprisingly enough, we get 2h over h. We can cancel the h's. And our average rate of change for that particular function is 2. Huh. Well, we'll do more of these down the road. This is the first try. Okay, let's start talking about lines a little bit. So if the rate of change of a function is a constant, if it's always the same, then the claim is the graph of that function is a line. So hopefully this won't seem like too big a stretch. So imagine I'm starting with a point that I know is on the function. And just to make it make sense, to give us something to wrap our minds around, let's suppose the average rate of change is going to be a negative 1. So that means from this point that's on the curve, if the change in y over the change in x is negative 1, then if I go down 1, change of y is negative 1, change in x is positive 1, that would take me to there. But I could also say that a negative 1 is negative 2 over positive 2, and so on. And the claim is that all of those points on that function, on the graph of that function, are going to form a straight line. Okay, so the takeaway is that this is a characteristic of a line. Okay, if the rate of change is constant, then the graph is going to be a line. If the function is linear, if it's a line, then its rate of change will be constant. So let's see how we can ask and answer some questions based on that fact, on that characteristic of straight lines. So again, I'm going to give you a potential. It's a function. A function has a table of values. So I'm going to say the t values go 0, 4, 8, and 12. And the q values are going to go 50, 150, 250, and 350. So the questions I'm going to ask you 3 of these here. First of all is, and you, if you want to, after I write them down, if you want to pause it and try to work them out yourself, you can do that and then see how well you did by continuing to play the video. Is q a function of t? That's the first question. Second question is q linear? And then, can you justify, or that is, why or why not? So can you justify your answer to part B? Okay, so here's the idea. We can see that all of the t values are different. Remember, so that means it's going to be a one-to-one function. It's not going to be one-to-many because we don't see any of the t values represented. So yes, it is going to be linear. Whoops. Write that. Let me try making that a little more clear. So the answer there is yes. It is a function. Now, is it linear? So to be linear, what we just claimed is the rate of change has to always be constant. So we need to look at some delta y's over delta x's. So here, the change in y's, the 150 minus 50 is 100 over the change in t in this case. I guess I should call that a delta t rather than delta x, but it's the same idea. That's going to be 4. Now, if I look at the change in, I guess I should have called that a change in q. So let me be a little bit better with my notation. So I'm going to call it delta q over delta t. So on the first one, it was 100 over 4. On the second one, 250 minus 150 is also 100. 8 minus 4 is also 4. And likewise, you can see on the third one that all of the rates of change are the same, and so that is why we know it's going to be linear. And the why it is because we can say the rates of changes are constant. That's a definitive characteristic of a line. Okay, let's try another example. So this time I'm going to give you x's and y's. And on this example, the x's are going to go 0, 1, 3, 6, 0, 1, 3, 6, and the y's are going to go 10, 40, 70, 100. So let me back up to the one we just did a minute ago. Another clue that this was going to be linear is you can see that all of the q values are going up by a constant. So 50 to 150 is up 100. We added another 100, added another 100, and the t values were also going up by a constant each time. That fact is what is leading to this rate of change, the delta q over delta t, being positive, because the q's and t's are changing by the same amount each time. Now you can see on this next one, I want to still answer the same questions, A, B, and C. Is it a function? Is it linear? And then why or why not? So here you can see that the y values are going up by 30 each time, but the x values are not going up by the same value each time. It went up by 1, then by 2, and then by 3. Now, first, is y a function So I'm going to say y a function of x. I'm going to ask that as a question. Yes, it is, because again, we don't see any repeated x values. So we don't have that one-to-many occurring that would make it not be a function. Is it linear? Well, now we have to look at those delta y's over delta x's. And if we look at the delta y here, 40 minus 10 is 30, and the delta x is going to be 1. When we do the delta y over delta x on the next pair, we again get a delta y of 30, but this time we have a delta x of 2. So immediately we know that no, this is not going to be linear. And the reason for that is the rates of changes are not constant. So that means it is not linear. Okay? All right, let me get a new screen here. Let's do this kind of verbal representation of our function. So I'm going to give you a word problem here. So suppose that the enrollment at Laramie High School, which we are going to call capital E, is 1,000, and also that it is growing by 50 students per year, is growing by 50 per year. So then what I want is to answer to ask some questions. And again, you can try these if you want to pause it. So what is the average rate of change? First question. Second one is enrollment a linear function of time? And thirdly, can you write a formula for the enrollment? So the enrollment in terms of the time t. So our rate of change, since it's growing by 50 per year, that means that our rate of change is constant. And so that means that the rate of change, that average rate of change, also known as our slope, is going to be 50. Is it a linear function in time? Yes, because that rate of change was constant. And then hopefully if we say, thinking in terms of y equals mx plus b, hopefully we can see that the enrollment is going to be, we're going to get our rate of change, 50t plus the 1,000 that we had at time 0, which is right now. And so there is our equation. Okay, second example, kind of similar. This is going to be depreciation. So we're going to say, suppose that a business buys $20,000 in new computer equipment. Buys $20,000 in new computer equipment. We'll also say that for tax purposes, this is commonly done with businesses. For tax purposes, we're going to say it depreciates, that is, it loses value. It depreciates to 0 at a constant rate over 5 years. So what I'm going to ask you for here is, can you figure out the rate of change? Can you write a table of values for that function? And can you come up with a formula for that function? And of course the answer is yes. So the average rate of change, since it's going from, the value is, so we're going to say the value depends on time. So the time is our independent variable, and that's going to be put in the x position. And the value of the equipment is going to be the dependent variable. That's going to go in the y position. So I'm going to say at time 0, this value of the equipment is 20,000. At time 5, the value of the equipment is 0. So our rate of change, again, we're thinking y2 minus y1 over x2 minus x1, like we would as a good Algebra 2 student here. So I'm going to say 0 minus the 20,000 over 5 minus 0. So that's going to be a negative 20,000 over 5. Since 20 divided by 5 is 4, that's going to be a negative 4,000. So just thinking units, because to get the practice, that's going to be dollars. That was the y value per year. Whoops. Let me write year. Okay, so the negative is not surprising because it's decreasing in value. So that price is going down from our 20,000 to 0. So a table of values. Let's do our table this way. We're going to say time and we'll say value. So at time 0, 1, 2, 3, 4, 5 years. And so this is going to be in years. And we can say this is going to be in dollars. So it's going to be 20,000 at time 0. It's going to go down by 4,000. I didn't space that very well. Let me see if I can do better. So let's say after 1 year, it's going to go down 4,000 in value. So now it'll be worth 16,000. After 2 years, it's going to go down another 4,000. So now it's worth $12,000. After 3 years, it's going to go down another 4,000. Now it's going to be worth $8,000. After 4 years, it's gone down to 4,000. And after the 5th year, it's down to 0. Okay, and then our formula. So we are going to say, let's say the value is going to equal, it's going to be linear, so it's going to be a negative 4,000, that's our average rate of change, times t, plus the value at time 0, which was the 20,000. Very good. Okay, so I'm going to assume that you are comfortable with the slope-intercept form of a line, and that is y equals mx plus b. So I'm not going to do any more with that. If you have problems on your homework, you can bring it up when we talk in class. But instead, I want to do some algebra review here because we have some kind of challenging problems here that I want to make sure that you're comfortable doing. You can do with accuracy. So this, again, we're going to solve for x in each of these scenarios. I'm going to give you 3 different examples. And again, you may want to pause it and try it on your own, because then otherwise I'm going to jump right into it and it'll take all of the fun away. So here's our first equation. So I'm going to say, let's get rid of that 5 in the denominator by multiplying each thing by that 5. So multiplying the 2x minus 3 over 5 will cancel the 5 in the denominator and just give us 2x minus 3. The x doesn't have anything to cancel, so that's going to become a 5x, and the 5 on the other side is going to become a 25. Combining like terms, that's going to make it be a 7x on the left side. Adding the 3 to the other side is 28. And in this carefully constructed problem, it works out nicely to be 4. Okay, here's a different one, challenging. Let's say we have 3x plus xy is equal to y minus 7. Now this is tricky because we're still trying to solve for x, but we've got an x in two different terms. So the trick is to factor out the x, leaving behind the 3 plus y, and then dividing that whole 3 plus y to the other side and getting that y minus 7 over 3 plus y. Now, it may be tempting to try to cancel those y's, but that is not correct. Don't do that. Okay, let's do one more example. And that's, again, we're going to solve for x here. So this time we've got x squared plus 3x is equal to x plus 6. Hopefully you remember from your Algebra 2 days that when you've got an equation with x squared, what we'd like to do is bring everything to one side of the equal sign and make that be equal to 0. Now we can try to factor that. Sadly, this does not factor. Fortunately, who could forget the quadratic formula? Don't answer that. I'm going to remind you of it. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Feel free to hum that if that's the way you learned it. And so we're going to get negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that's negative 2 plus or minus the square root of. The two negatives make that a positive. So 4 plus 24 is 28. Of course, we're not satisfied here. We remember that you must simplify that square root of 28 and think of that as 4 times 7. And so that's going to become negative 2 plus or minus 2 square root of 7 all over 2. And of course, we can split apart that fraction. Hopefully we're getting the rust off from our long time off. And our final answer is going to be that x is equal to negative 1 plus or minus the square root of 7. Very good. You can give homework number 4 a try.